Hello, I am Paweł Pomorski, and I'll be talking about automating scientific workflows with AiiDA. So first, what is AiiDA? It stands for Automated Interactive Infrastructure and Database. And this is the this is the website address if you want to explore it more. It is an open source Python infrastructure to help researchers with automating, managing, persisting, sharing, and reproducing the complex workflows associated with modern computational science and all associated data. Initially, it has been designed for computational material science, and most of the plugins currently available are for that family of software, but it can definitely be extended to other areas. And this is a tool which is meant to be installed on your laptop, on your desktop, on your lab workstation, from which you can control clusters. You can send the job to clusters. So this can be installed on the Linux machine, on Mac OS. That's the one I am using. On Mac, you have to install some kind of a Linux package manager. I'm using Homebrew. And you can also install it on Windows using the Windows subsystem for Linux, which is quite convenient to use. So let me also mention some alternatives. So AiiDA is not the only tool available, though I will argue that it has some advantages over these other tools. So there's AFlow. This is for material science calculations over a large database of structures. So let's say you have thousands of different crystal structures and need to calculate some properties over that. AFlow would be a good tool for this. There's also atomic simulation environment. This is meant for single calculations only, but you can do quite sophisticated workflows for material science. There's the software called Fireworks, which is actually workflow software. It's a general workflow software for running high throughput calculation workflows at supercomputing centers. And then there's Automate, which actually uses Fireworks, and also PyMatGen and Custodian, which is so PyMatGen is a material science suite, and Custodian is a job running package. So I will not say that much about these alternatives because I don't know much about them, but I'm just listing them here. And presumably, if you are in the field of material science or just in the field of research computing, you might have your own scripts. Sometimes a group writes their own scripts to manage their workflow, and that is fine up to a point, but those scripts, you are redoing a lot of work that other people have done, and also these scripts are unique to your group, so they might not be easily shareable and so on. So at the heart of AiiDA are workflows. So the reason you would want to use a tool like this, if you are just running a few jobs on a cluster, then you can probably do it all by hand, and that's probably the most efficient way. So you don't need software like this. But as your workflow becomes more complex, and as you're running hundreds of jobs or thousands of jobs, and as you're running into multi-step procedures so that one job depends on another, it very soon becomes impossible to do it by hand. And as I said, you can write your own scripts, but that works up to a point, and eventually that fails as well. So AiiDA offers you the full power of Python programming to develop workflows. And you run these workflows on your local computer to launch arbitrary executables on remote compute resources. The really nice thing about AiiDA is that you can use multiple computer resources and not just one cluster, but you can connect to multiple clusters, and AiiDA will very smoothly handle this case. And once you specify your workflow and you submit it, then the AiiDA daemon running on your computer will handle everything. It will handle its execution, it will monitor what's happening to your jobs, it will see when the prerequisite jobs are finished before launching subsequent step, and so on. So it is a kind of intelligence which runs the workflow on your computer. And you can chain these workflows, so you can allow users to group their code into functional building blocks and combine them in sophisticated simulations. And you can share these workflows with others as well by contributing them to a workflow library. Another key part of AiiDA is plugins. So these are basically the interfaces between AiiDA and a particular software that you're using. So an AiiDA plugin will take care of preparing input files for the simulation and parsing the output into AiiDA data types. There's a public AiiDA registry to find AiiDA plugins, because some of these are quite complex, because some software is quite complex. Users can also develop their own plugins, though admittedly, it is not entirely trivial. It takes some knowledge of the AiiDA interface to do this. And I looked at the plugin list just recently, and I see on this list Abinet, Castup, CP2K, Gaussian, GROMACS, LAMMPS, Orca, Quantum ESPRESSO, VASP, which I'll be using for my demo, VN2K, and so on. So all the most common materials, quantum chemistry software is out there. Not everything. I mean, for example, I don't see NAMD in this list, which is another popular molecular dynamics program. And also, I cannot vouch for the quality of these plugins. Some of them might be more developed than others. I mean, some of them might still be work in progress. And actually, there's even a plugin to enable the use of fireworks and ACE. So these workflow software, which I mentioned before, they can actually interface with AiiDA. So for example, you can use fireworks to launch jobs on a cluster to control the launching of jobs inside AiiDA. Now, the key thing that AiiDA offers is the HPC interface, so it can interact with multiple HPC clusters. And once you have an HPC cluster set up as a computer with an AiiDA, you can change one line of code to send your job to a different cluster. So this is, I would imagine this would be something extremely useful to Alliance users, because in our setup, we have multiple clusters. We have Sierra, Graham, Niagara, Northern, Beluga, and all of them are independent from each other and have independent schedulers. So it's nice to have the flexibility that, let's say you have some jobs on Graham and you find that jobs are waiting a long time there because Graham is busy or because you used up your priority on Graham. It would be really nice to have an option to submit your job to Cedar. And right now, that's a bit tedious because you have to move your files by hand, you have to submit jobs by hand, and if your jobs are part of a single workload, then this workload will be distributed on many different clusters, and that's inconvenient to organize. But with AiiDA, it should be possible to just change a single line in your Python script or notebook, and the job will go to a different cluster. So that's quite useful. And then AiiDA will download and combine results from different clusters without any problem into a single set of results. So it's really convenient because once a calculation is submitted, AiiDA takes care of all the details. It uploads the data, submits the job, downloads the results once the job is done, and cleans up the job directory on the cluster when the job is finished. So another key feature that AiiDA offers is reproducibility. Because in AiiDA, data provenance is tracked automatically. Each calculation that you do and each input and output object will be represented by a node that is linked to its input and output data nodes. So this results in a provenance graph, which is stored in the local database, and you can query it using a performant high-level Python interface. So this means that if you do your work in AiiDA, and you ask yourself 1 year later, how did I get this number? How did I get this result? You will be able to track down all the calculations which led to that result. And you can rerun them if you need to. So that's quite good. And you can also share this by exporting the provenance graphs. So let's say you publish a paper and you have a provenance graph for all the calculations that you did. You can share this. And if somebody wants to reproduce your results, they can download it, for example, from Materials Cloud. And somebody else can rerun your results, or they can just continue your work exactly where you left off. So that can be a quite powerful tool. And this data can be queried. So if you switch to using AiiDA and you use it for a long time, you will accumulate a pretty large database. But fortunately, AiiDA provides a powerful querying mechanism to search for data. So for example, for a given node, you can determine which other nodes have used it as input. So which nodes depend on this node. So for example, if down the line you realize that there was some kind of a problem with the calculation for a particular node, you used the wrong parameter or program was compiled incorrectly, whatever, like this, you will be able to actually find which other nodes depend on that node. And so then you know which calculations need to be redone with a corrected data or corrected software. So this really gives quite a lot of power when it comes to fixing, correcting your own calculations and tracking down if something goes wrong. So now I'm going to switch to my notebook. and I'm going to give you a little bit of a demo of what AiiDA looks like. I am actually fairly new to AiiDA. I have only been using it for the last few months, so I'm by no means an expert, but I hope to give you a flavor of how it works. I put everything in a notebook here just to keep everything in one place. This is not necessarily the natural way to use AiiDA. You might want to do some of these things in a terminal, might be easier. Okay, so first, how do you set up AiiDA? I'm not actually going to go into any great detail, except to say that this is something fairly easy. You install the required Linux packages and you start the required services. AiiDA installs with a pip install once it's available. And then once AiiDA is available, there's a executable command line interface called Verdi. By the way, you know, if you're a classical music fan, then AiiDA is the opera and Verdi is the composer. So that's where that comes from. And so you also need to create an AiiDA kernel to run inside the Jupyter notebook. Notice that here I'm using the AiiDA kernel, which is just a notebook kernel, which includes the virtual environment that AiiDA was installed into. And once you have done all of this, the first thing to run is the command Verdi status. And this just tells me how Verdi is doing. So it shows me the version, shows me the profile I made, which I made with quick setup. So Verdi has a quick setup profile, which just connects to the default database. It sets up the database it needs and so on. So for example, here, this is showing me that the storage, so the database it's using, it's a Postgres database running on my local computer. I get a warning about RabbitMQ, which I'm not going to worry about now, but in principle, there's some version incompatibility which could cause issues. And once this is done, then I can start using AiiDA. And as I mentioned, Verdi is a command line interface, so I could run this from a terminal, but here I'll be running it from inside the notebook by using, you know, the exclamation mark, which allows me to run these commands inside the notebook. So first, let me discuss nodes. So everything in AiiDA is a node, any input, any output. And each node gets a unique identifier and it gets tracked in the database. So the simplest thing to do is let's just create a node which has a single integer in it. So we from AiiDA, we import the object manager. I think that's what it stands for, more or less. And I create node 1, which I make it an integer node, which is initialized with 2. I run the store method, which actually puts it into the database. And then I print it. And this tells me information about this node. So this node has a unique identifier and a specific number within the database and a value. So I have been running this database for a while now. So I'm already up to node 1387. And let's say I want to now perform some calculation on that node. So I can, let's say I just want to multiply two numbers. So I can define an AiiDA function. It just multiplies two numbers, returns x times y, and there's a decorator from AiiDA. And let me now multiply two numbers. So what I'm going to do is I'm going to, let's say I want to multiply x times y. So for x, I'm going to take node 1387, which I created here, and I'm going to load it. So basically, I'm going to get the value of x from that node. And I'm going to create node y, which I'm just going to initialize with integer free. And I'm going to call multiply. So notice what this does. This actually doesn't have a return, but that's OK. When I call a function created in this way, this will automatically store the result in the database. And here it's telling me that the result has been stored in node 1390 and the value is 6. Note also that even though I did not store y in the database, it got automatically stored in the database. So if I print the value of y, it's showing me that it also has a database identifier. So AiiDA is smart enough that if you run a calculation, all the inputs are stored into the database. And then I can use these nice visualization tools to actually get the relationship between nodes. So here, I can run a graph visualization on object 1389, which was my calculation. And I can see that the input value 2 and 3, these were the input nodes, and I see their indices. And I can see that the output node is here, and I can see its index and the values. So this is, of course, the simplest case, but I can see how my data is flowing through the nodes. So what are the input nodes? what is the calculation node and what is the output node. And notice here that, 1389 wasn't printed, but I could run this same graph on 1390 and it would show me that it's coming from here. So, if I run this on 1390, it would show me just these 2 bits, but I could then find out it comes from 1389. So I could then do the display on 1389. And so that's one way to view a node. I can also actually show a node. So I can run Verdi node show, and then the identifier of the node. And this tells me everything I need. It tells me that, what did I do? I called multiply. It is finished. So the status of it is that it is done. It has the ID within the database. It has a unique identifier, which I can also refer to it that way. Tells me when I did the calculation, and it shows me the inputs and the outputs. So even a simple calculation like x times y, I have stored all the information about it. And of course, in real life, I would do more complex calculations, but the principle is the same. Okay, so making things somewhat more complex, let's now look at a very specific calculation of using VASP. So this will be a real quantum chemistry calculation on a very simple system, which I will first do without AiiDA, just to show you what is involved, and then I will do it within AiiDA using the AiiDA plugin. So, I'm going to be using one of the standard examples for VASP, and VASP, if you are doing a simple calculation, VASP runs just needs 4 input files. So they are here: incar, kpoints, postcar, podcar. So incar, this is the input parameters. So I looked inside that file here. So these are its content. By the way, ignore this annoying message which I get. It's just something that is associated with the special account I'm using for this. We just didn't clean up this error message, so you will not see it. So there's 4 files, and here I look inside the input incar file, and there's some 4 parameters for running this. And then I run my VASP executable. In this case, I just did by hand, not even because it's a tiny job. So I didn't even do it inside the job. I just logged into Graham and ran it beforehand with mkrun. And once I run it and I list the files after I run it, I can see that it created a whole bunch of VASP created a whole bunch of output files. And the key one is outcar. This is the standard VASP output file. And then I can look inside it and, for example, grab for free energy. I mean, this file has about 1,500 lines. I'm going to print the whole thing, but these are the energy values I get. So this is what the energy converges into at the end, the last line. So basically, this calculation, I take a periodic crystal structure of silicon and I compute its energy. So this is how I would do it by hand without AiiDA. So let's now look at how this calculation would be performed by AiiDA. So as we will see, it will be somewhat more complex. I mean, the setup to get this going with an AiiDA requires some lines of code. So if you are doing a single calculation, if you're just doing only one calculation, it's probably easier to actually do it by hand. But as we will see, once we have this code figured out, we will be able to do multiple calculations, and it will be more efficient to do multiple calculations with AiiDA than by hand. So some setup is required now. So even though I have installed AiiDA, I now have to set up some computers that I can use. So because AiiDA will be running on remote machines, you can, of course, run AiiDA on your local computer as well, but I'm not going to cover that. I'm just going to cover running remotely. So I have already set up some computers. So if I run Verdi computer list, it shows me the computers I have access to. And I have a computer I have set up, which I call Graham1 and the Graham service. And here I could have added other Compute Canada clusters. I could have added Cedar. I could have added Niagara, whatever I wanted. And you can also have different settings, different accounts for these computers. So for Graham1, I have my own account, and for Graham service, I'm using a service account, and which is basically a special account for running a certain type of jobs. So I'm going to use Graham service. I can test this computers. I can run Verdi computer test Graham service, and it mostly passes the test. There's some spurious output it doesn't like because I'm getting this silly message cannot find group name, which is innocuous. So it throws a warning, but it's mostly happy. And if I want to see how this computer is set up, I can do computer show. And here it shows me that, this is the host name. This is the transit time connecting via SSH. This is the work directory. This is the standard command to run MPI jobs, and so on. So, so this is my setup for the computer, and it's pretty straightforward to set up any computer like this if you have an SSH connection with a public key available. So once you have a computer set up, so that's one entity you're using with, and then the second entity will be a code on this particular computer. So here I'm going to list the codes I have available, and I have 2 codes, and let's say VAS, I can of course call them whatever I like, but looking at VAS Graham at Graham_service, I can see that this code has an identifier, so this code is actually an object in the database as well. Here I indicate which computer this code is running on, and I need to have this code installed at that computer, so I need to have an executable installed at that computer, which I can point AiiDA to. So AiiDA doesn't upload its own executable. You have to log into the target machine at least once and set up your executable. Then I have some labels, and here I can prepend text. So when I run this code, if I need certain commands to run, and here I do need to load some modules, I can add those commands in the preamble. And then actually, if I wanted to, I could have some append text. If I want to do some debugging on the output files, for example, if I want to copy the output files to somewhere and look at them, I could put some text there. So generally, if everything goes well, AiiDA removes the job files which existed while it was running. But if there's an error, then AiiDA by default keeps those files around. So you can look inside those files and see what was going wrong, what has gone wrong. So that's pretty convenient. And the final step here, which I'm not going to show, is you need to upload the pseudopotentials. So if you're running any kind of quantum chemistry software, there is a set of pseudopotentials for each atom you need to upload. And here, there's a step which uploads those files for VASP automatically. Okay, so now let's look at the first example of AiiDA. So this is one of the AiiDA tutorials. And this is just an implementation for, exactly the calculation which I have shown you before done by hand, but within AiiDA. So, so first I'm going to import, a bunch of standard modules called load profile. That's an important step. And then I need to have a function to create a structure. So for silicon, which we are simulating here, you have a face-centered cubic. So this has 4 atoms per unit cell. And here we just fill them up. So so anyway, so I create my structure. I wonder, this actually doesn't look like FCC. It actually has maybe this is actually SI2 structure. So sorry about that. But anyway, so I set up some kind of a structure. And in this case, it's just a constant structure. So it just has a certain standard parameters. And then here is my, well, maybe I should actually jump to the code, which is run if this is run as main. So I have to set up a whole bunch of input parameters. So I specify the code string. So this is the code which I have set up before. So I specify I'll be using that. For the structure, I call getStructure to get my atomic positions. For the input parameters, I provide a dictionary. So this is the stuff that will go into the incar file. I have to specify the k-point mesh. I have to specify which potential I'll be using. So I specify potential family and potential mapping. So potential family is PB, and potential mapping is I'll just be using silicon. And then here I have some optional arguments. So these are arguments for the job submissions. So what will be my runtime, wall clock in seconds, how much memory I need, and so on. And here I'll be calling the main function with those options. And then here, the main function actually translates these parameters into AiiDA objects. So for example, I have to import from AiiDA the dictionary data structure to store dictionaries, and then array k-points to store k-point data. I have to, and then here I'm invoking the default VASP work chain. So, the VASP plugin offers different work chain. This is the default and most general one. And I also here specify some parser settings for outputs. So AiiDA generally preserves all key output files by default, but you can also specify some specific parsing of the output if you want specific values in particular. So the AiiDA plugin has a list of values you can parse. And then here it's basically some formalities of AiiDA. We have to take all these parameters and translate them into objects which AiiDA understands. So we have to create a code objects in the inputs node, structure, k points, and so on. And finally here we get to the point where I can submit the work chain. So I call submit, and then work chain, and then inputs. And this actually launches the workflow. And the results will be sent to an output variable, and then I can print the output. Again, it's not essential, but this will nicely give me the name of the node which this workflow is using. So anyway, so here I execute this block, and it tells me that it has launched this workflow. So and the index of the workflow, I get the process index 1434. So this just launches the job. So this cell in the notebook immediately finishes, and now I have to see, well, how are my processes doing? So now I can call Verdi process list, and this will tell me what my processes are. So here I have some older processes which we can ignore for now, but process 1434 is here, and I launched this command just a few seconds after I executed the cell, and it was in the waiting state. But then I logged into the Gram cluster with SSH, and I launched the SQ command, and so this was a few minutes later, just to see are any jobs running. And in this case, there was no job. So the job which the workflow actually ran has finished. So I was all done there. And here I can, so actually any of the processes here, I can also query their state with a process report. So here I'm going to run a process report on that chain number 1434. And here it's basically showing me that this chain is done. So it shows me that this time it launched the VASP calculation. At this time, the work chain completed, and at this time, the remote folder was cleaned and the data was copied back. So the important thing is that it always takes a little bit of time to actually submit the job and process the results, especially if if the cluster is busy, if the job has to wait for a while. So before trying to see the output, you should first make sure that the job has actually finished. But anyway, I can actually look at the node directly. So here I have Verdi nodes show, and I look at the VASP workchain node, and this tells me everything. This tells me what the inputs were. So there's actually many inputs because they belong to different objects. So for example, options, max iteration, k points, and so on. And the outputs, so the outputs, I have the MISC output, which will contain the parser output data I specified. But the important one is the retrieved folder data. So essentially, when VASP runs, it automatically transfers all the key files like outcar and some other important output files. You can actually, if you want some additional, so it doesn't transfer everything by default. So if you want to have some additional files, you can specify them explicitly. And so this is our entire calculation and all its data points. So for example, if I want to see what is the retrieved data, which is sitting in node 1438, I can do node repo ls, and here I can see the files. So here I can see which files have been copied from the calculation. So I can see not everything has been copied, because if I roll back a bit, then these were the files which I got when I was running by hand. So there's definitely more of them than the files which I got transferred, here. But anyway, but outcar is the key file, and if I want to look what is inside this file, I can do Verdi node repo cat and then 1438 for the node and the name of the file I want, and here's the entire output file. So this is nice because the entire file of the calculation is stored for future reference, and these are just text files, so they generally are relatively small, so they are not going to fill up your database that quickly. Now, of course, I can imagine if you had a larger data file, like a trajectory file or something like this, then presumably this would stop being practical. I mean, you cannot store, you might run some data limits, but definitely for small text files, it's fine. And then I can also use the visualization tools. So for example, let's take a look at the provenance of the folder data. So folder 1438, I can call these visualization tools here, and it shows me that the folder data came from the VASP calculation node 1436 and the VASP work chain 1434. So this calculation used the work chain, so they were both, so both the work chain, which again exists as everything in AiiDA exists as a node in the database, and the work chain does as well. So I can see that both of these contributed. And I can then look at node 1434 and node 1436. And here I can see the full complexity of what's going on. So here is my work chain, and this produced folder data. It produced the MISC object, which is a dictionary. The remote folder, it's actually the name of the I believe it's the name of the directory on the cluster that this ran in. So, if you're interested, like which directory was used, even though I think that directory will be left empty. So the data is removed just to clean things up, but you do have an empty directory there. And this also went into a VASP calculation. And here I have all the various inputs. So this was the work chain, and this is the provenance graph for the calculation. So I think the work chain has more inputs because the work chain is more general, whereas here we have the inputs for a particular calculation. So again, if I, for example, wanted to see what K points did I use, I could query this particular node. What structure data I use, I could query this particular node, and so on. So this is, so you can see and of course, if you had a multi-stage workflow, then this provenance graph could potentially grow really complicated. And I can print the results directly. So let's say if I'm interested in total energy, I can take node 1434. Again, node 1434 was well, and it was so looking back here, it was well, actually here I might be using an incorrect number, but anyway, because I ran this node multiple times, so maybe I'm using a previous node. So if I change this to 1439, no, it doesn't work. So let me try to track this down. Okay, well, okay, this is the VASP work chain. So I'm using 14. Okay, so I'm using the work chain here. So 1434, and I'm loading this up, and I'm looking at the MISC object, which is connected to work chain. So yes, so I'm going to be accessing this object here, and I'm accessing it by name, not by node number. I could also do it by node number, but here I load the node, I look at the MISC object, and that is a dictionary. So I can print the entire dictionary, and this contains some standard information about the job, user, how long it took to run, how much memory was used, and so on. And then for the stuff that I want to query, it contains energies. So energies in particular, that's what I'm interested in. And here I can access this dictionary and print total energies, and I get the total energy of the system. And I could also query input files in the same way. So for example, if I load the same node, but now I look at the parameters object, this will show me the input files that were used. Okay, so this is how I would do a single calculation with AiiDA. And you can see it's a little bit tedious. I mean, like in real life, if you were running just a single instance of VASP, it probably would be faster to upload the files by hand. But now let me show you how I can do multiple calculations. So this is actually, it's a little bit of a different problem than what we have seen before. Now this is a true FCC structures because there's 4 atoms in the unit cell. What I want to do here is I want to basically try different unit cell volumes and compute the energy for particular volumes of the unit cell to find the minimum, and the minimum will correspond to the true volume of that crystal. So now I have a get structure function which takes a parameter, And this parameter is just a scaling function, which shifts the atoms depending on how I change the volume of unit cell. The main function is similar, except now I don't use the default VASP work chain. I use a relax work chain. So if you have a standard calculation like relaxation of a structure, then there's a specific work chain provided for this. And this allows you to provide some parameters specific to relaxation. So for example, in my case, I'm going to allow positions to be relaxed. I'm going to allow the shape of the unit cell to be relaxed, but I will keep the volume of the unit cell constant. So this will allow me to try different volumes. Here I specify relaxation steps, so how many steps I want to be performed. So the way relaxation works is you keep adjusting the atom positions until the energy change falls below a certain threshold, and then the structure is considered to be relaxed. So it's similar to what we have seen before, but there is just a few more parameters. But the important thing is here. So here's my main function, and many things are similar. My code string is the same as before. Input parameters very similar. But once I get to actually launching the job, I have a loop over lattice constant. So so I will try different values of the lattice constant, and I will create, so for each iteration of this loop, I will create a different structure. I will call get structure with a different lattice constant. And remember that the way we defined it here, this is the input lattice constant, and this multiplies the positions of the atoms. So I am rescaling my unit cell. And so now I create a bunch of calculation nodes, one for each one of these values. And here, as I do the calculation for each, I append the output list to output nodes. That's my list of the nodes. I also append the lattice constant to a list. And so here, after I run this code block, I can print the output nodes, and here I can see all the nodes which were created and their numbers in the database. So initially, you know, these nodes are not ready. So for example, after running this code block, I can look at the list of processes, and I can see that many things are going on. AiiDA is trying to submit jobs. There's many processes now because I have 9 different calculations, and each one is creating multiple processes. And then if I look at what is going on in the cluster a little while later, so here I log into the cluster and I run SQ, and I can see that, you know, this has created 1, 2, 3, 4, 5, 6, 7, 8, 9 jobs. It has created 9 jobs, and currently they are in the waiting state. I mean, they were when I ran this. By the way, you can also see that the name of the job corresponds to the database index. So I can see, for example, that here was job 1709, and that job, but actually does it. Maybe it doesn't correspond to exactly these indices. So, but anyway, so maybe because maybe these are work chains, and maybe this launches workflows. But anyway, the numbers here should correspond to some objects in the database. And here I am checking it again, and now I can see that the jobs are queued. So I did this a little later. But then at some point, they were finally done. And once they are done, I can actually look at the data. So for example, I can now look at all my calculations which I submitted. So for example, my output nodes here, this was the list of the calculation nodes. And I can loop over that list. Now for each element in the list, I can extract the, so I have a list of nodes, and I can actually extract the identifying number for each node by applying the .pk method. And so here, basically, once I have the node, I can load that node. Once I know its identifier, I can get its output dictionary, and I look at the total energy. I can look at the total energies. And so I can print the, from the list of lattice constants, I can print the lattice constant and the energy. And here I have results for all the different lattice constants. And of course, I can plot these results now. So I'm just going to do matplotlib plot. And so I can see that this is the free energy for different lattice constants. So you can see here what I have done. I have run 9 different VASP jobs. And if I had tried to do this by hand, that would have been quite tedious. I would have to have created 9 directories, generated 9 different structure constant files, submitted 9 jobs, collect the results. But here, everything is happening in one place. And let's also note that when I'm launching these jobs here, I launch them with the same computer. But if I had access to different computers, then I could have, for the code string, I could have specified a different code string. So for each iteration, so potentially running some of them on different clusters, and the results would have still been collected in exactly the same way and printed out as I did here. So the final thing I want to cover is querying the results, because you can sort of see that the way I did things here I launched a calculation, and then I could immediately see what its identifier was, and I could reuse its identifier. But in real life, you might launch these calculations and walk away for a week and lose your notebook or not save it. So then how do you actually get your data after you're done? So one essential part of AiiDA is you have a complex mechanism to basically do all kinds of queries on these nodes. And I'm just going to show you a quick preview. So for example, I can, first of all, I am curious, how many nodes are there in my database? So I can count just all the nodes. How many nodes in total are there in my database? And at this point, there's 1,700. And then I can see how many calculation nodes. There's 35. So during this testing for this workshops, I did some calculations before presenting these results. I did a total of 35 calculations. And then I could search within this. So for example, I could search for calculations done within a certain time window, as an example. And really, I could do all kinds of queries on the calculation which I did, which hopefully should allow me to find the calculations that I'm interested in. And of course, the other way to do this is, you could say, as you're submitting jobs through AiiDA, you could actually just save your node numbers. I mean, for example, when I generated my nodes here, if I want to pick up this work later, I could have just written them to a file. It's also possible. But it is in principle obtainable from a database. And you can also ask questions. You can also look at structure. For example, in the second example, I can just look at all the nodes. And in this case, I'm actually looking at structured data. So certain objects are labeled as structured data. So I can just see all of them, right? So then if there's a particular structure which I was working on, I can identify it and look at those nodes in particular. So for example, I do a query, show me all the nodes which did this structure within the last 3 days, or for example, and this would hopefully bring you the calculations that you did. And finally, you can also look at the relationships between nodes. So for example, you can take a particular node, like 1434, our calculation node, and see what were the incoming nodes. So what were the input nodes which contributed to the calculation. So again, and you can look at output nodes as well. So this allows you to look at relationships between nodes if you need to fix something or change something. Okay, so I'm going to stop here. Hopefully this gives you a preview of AiiDA, and I hope that this really clicks with some of you and you might be interested in trying this out. And I'll now take some questions.